Okay, so we have the cubic Schrodinger equation, okay, that we said that it was proposed in a chess, and we also proved that QU was constant and QU was the norm U 202, and then we got HU, the Hamiltonian, was also constant. It was 1.5 integral Ux squared minus or plus, depending if it's focusing or defocusing, integral of U fourth dx. Okay, and remember that we had local well closeness. For example, if we have one dimension, then S is greater than 1.5. Okay, so for example, we had well post for H1R. Okay, so an important question that I never mentioned about is how can one derive, for example, here 2 times in one dimension in X, having only H1 functions. That means that we have only one derivative in O2. Okay, so we know that if U naught is in H3 of R, okay, then the solution U is going to be in C of 0t t, as we mentioned, t star that depends of U naught H3. Okay, and we will also mention the integral form of the equation. Okay, plus I 0t W t minus s U s squared US. Okay, and so we have that this is a polynomial function in H3. Okay, so this is going to be here in this space. Okay, so if we talk about one dimension, we will have the operator dx2, okay, that we can see that goes from H3 to H1, okay, after deriving 2 times, self-adjoint, okay, and so for example we can say that we have a U naught n, okay, so this U naught n will be in H3. Okay, I've been putting it down, I'm going to put it up, H3. So we can make a density argument. We can say we have a U naught n in H3 that converges to U naught in H1. Okay, so, and then we are considering Q and H continuous function that goes from H1 R to R continuous. Okay, so if we have a T star that depends on U naught positive, okay, we are considering that we have a t between 0 and t star that depends on u naught. Okay, you can see that it exists, let's say, on n naught, such that t star u 0 naught, okay, is greater than t, okay, and the norm of u n t, okay, minus ut norm h1 is less than epsilon if n greater than n naught. We consider t small in 0t, okay, and we can say that h of ut is equal to the limit when n goes to infinity of h of unt, and this will be equal to the limit of h h of u naught n, okay, and this will be equal to h of u naught. So in this way we can now consider a sequence of functions that converges to the u naught that we had in h1, but this sequence of functions are in h3, which this sequence of function represent a given function in h1, and then one can derive 2 times and obtain an h1 function. And now yes, we can say that we have solutions in h1 for the nonlinear Schrodinger equation cubic. So let's talk about global existence, and so we can recall we had q of u, let's say 1/2 of u squared L2, and hu equal to 1/2 ux squared L2, and then depending on if it is focusing or defocusing, we had plus or minus u fourth L fourth. Then if we take into account the plus case, okay, it's the case of plus 1/4 u4L4 is just the defocusing, okay, and so we have that the norm u squared L2 is equal to 2qu. This by conservation law will be q of u naught, and we have that ux squared, let's put the square down, L2 is well, less than equal than 2 times hu. Okay, so what it is, 2 times hu will be multiply this by 2, Okay, so 2 times HU will be UX squared L2 plus 2 times U4 L4, the positive, or at least greater than equal than 0. So we got this, and this is again equal to 2H U naught for conservation because of conservation loss. So we finally got that we can bound the solution in H1, taking in consideration both of these conditions. We have that the norm of the solution in H1 is bounded by 2Q U naught plus HU naught. So it is not the case that on the limit of t going to t star depends on U naught of the norm of ut h1 equal to plus infinity, okay, because we can bound that. Then because of the theorem it must be t star of U naught is equal to plus infinity. Okay, so what about the focusing case? 1/2 norm ux minus 1/4 of norm u fourth normal 4. Okay, so recall a result that we had, that we could bound a function f by the normal p by a constant, and f1 minus theta dsf theta, and theta was equal to n over s 1 minus 1p. Okay, we will use the case where s is equal to 1, p is equal to 4, and n is equal to 1. Okay, we're in one dimension, and we'll obtain that the norm f of L4 to the fourth is less than equal than a constant f third L2 fx L2. Okay, so we will use this to bound the part of the Hamiltonian that has L4 to the 4. So we can bound what we had, this, by the property that we saw, by U naught to the third L2 ux L2. So now we're going to use that a multiplied by b is equal to a multiplied by b, but having the square root of epsilon, and that this is less than equal than a squared over 2 epsilon plus epsilon b squared over 2, and we apply that to the term that we have, we will obtain c squared u naught to 6 2 epsilon epsilon over 2 ux squared L2. Using that, one can prove that h u naught plus c squared over 2 epsilon norm u naught squared L2 is greater than or equal than 1/2 1 minus epsilon norm of ux squared 2. So we wanted to bound ux, we can bound it by this. So the norm uxt squared L2 is bounded, and we know that ut squared L2 is bounded. So then we have that ut squared h1 is bounded. That is what we wanted to see.